everyone. Welcome to today's webinar. This webinar is being brought to you by the Energy Storage Technology Advancement Partnership, also known as ESTAP. And our topic today is the U.S. Department of Energy Office of Electricity's Energy Storage Safety Plan. And to begin with, I'd like to go over a few quick housekeeping notes. All of our participants today are in listen-only mode. This means that you can hear us, but we can't hear you. You can use your telephone to participate in the audio today, or your computer, mic, and speakers to avoid toll charges. And we encourage everyone to please submit your questions throughout the webinar into the question box on your webinar console, and we will queue up all of your questions and answer them at the end as time allows. So again, please submit your questions as you think of them. Don't wait till the end. And finally, this webinar is being recorded. You'll find a recording of this webinar and all of our previous CESA webinars archived on our website at the address you see on your screen, cesa.org/webinars. And with that, I'd like to pass this over to Todd Olinsky-Paul. Todd is our ESTAP project director here at CESA, and he will be introducing our webinar today.
Thank you very much. And I would like to welcome everybody to this ESTAP webinar. We are going to have a very good attendance today. Expect somewhere around the neighborhood of 100 people, and we're very much looking forward to it. We have 4 excellent presenters. Before I get to the introductions, I'm going to say a couple of words about the ESTAP program. Go ahead and advance the slides, please. In doing that, I wish to thank Dr. Imre Gyuk, who is actually one of our presenters today, from the U.S. Department of Energy, Office of Electricity Delivery and Energy Reliability, who funds our ESTAP program, and Dan Borneo of Sandia National Laboratories, who is our program manager at Sandia. Next slide, please. So in introducing everyone to ESTAP, if you're not aware, ESTAP is a project of CESA. CESA is a nonprofit organization. We work with states primarily on clean energy programs and helping them with policy and programs that they implement. ESTAP is conducted under contract with Sandia National Laboratories. This is our energy storage program, and we have 2 key activities under the ESTAP program. First of all, we disseminate information to stakeholders, and secondly, we facilitate public-private partnerships at the state level to support energy storage demonstration projects. And what that means is that we bring states to the table to partner with United States DOE and with Sandia National Laboratories to deploy energy storage around the country. And you can see on the map a few of the projects and programs that we are working on at the moment. Next slide, please.
Slides are not advancing.
There we go. Thank you. So I wanted to point out that we do have an ESTAP webpage on the CESA website, and 2 particular points. One is that if you are not signed up for our listserv, if you got notice of this webinar through a colleague or a forwarded email or something, you can go to our website. There's a big green button with a red circle around it on the screen, as you see. You can sign up and get notices of future events such as this, and we do have these webinars regularly. Also, I want to point out on the menu on the left, there's a red arrow indicating where to look for our webinar archives. And yes, this webinar will be archived along with all the other webinars that we've conducted over the past several years, and you can review them at any time. Next slide, please. So I think that that concludes my bit, and I will then I will give a brief introduction of each of our speakers. I just want to note that we have 4 speakers today, and then we will address questions from the audience. Please type your questions in as they occur to you, and we will do our best to get to all the questions that we can. So today's guest speakers in order, we have Dr. Imre Gyuk, Energy Storage Program Manager in the Office of Electricity Delivery and Energy Reliability at the U.S. Department of Energy. Dr. Gyuk joined the Department of Energy to manage the Thermal and Physical Storage Program. For the past decade, he's directed the Electrical Energy Storage Research Program in the Office of Electricity, and he also supervises the $185 million ERA stimulus funding for grid-scale energy storage demonstrations. He holds a BS from Fordham University and a PhD in theoretical particle physics from Purdue University, and is internationally recognized as an expert on electricity storage technologies. Then we will hear from Dr. Sean Hearne, Manager of the Energy Storage Technology and Systems Department at Sandia National Laboratories in Albuquerque, New Mexico. Sean is the Program Manager for the DOE Office of Electricity's Energy Storage Program at Sandia. He holds a bachelor's degree from Embry-Riddle Aeronautical University and a PhD in solid-state physics from Arizona State University, and he was previously a senior process engineer at Intel at their components research group. We will then hear from Kenneth Willette, Division Manager of the Public Fire Protection Division of the National Fire Protection Association. Ken manages a technical staff that supports over 90 standards addressing the needs of the fire service and emergency responders. He has 35 years of experience in the fire service and emergency preparedness planning, having served as an airfield and structural firefighter, a shift commander, and chief of department and emergency manager for 2 communities. He earned a BS in Fire Protection Administration from Empire State University, graduated from the Executive Fire Officer Program of the National Fire Academy in Emmitsburg, Maryland, and is past president of the Fire Chiefs Association of Massachusetts. And finally, we will hear from Dr. Vincent Sprenkle, Manager of the Electrochemical Materials and Systems Group at Pacific Northwestern National Laboratory. Vince also manages the Department of Energy Office of Electricity Energy Storage Program projects at PNNL. So we will begin, as I said, with Dr. Imre Gyuk of US DOE, and I will now pass the baton to him.
Okay, well, welcome to our webinar, and today we are going to talk about safety in energy storage systems. Specifically, we are going to address the Office of Electricity Energy Storage Safety Strategic Plan. Now, right off the top, this is not to say that energy storage systems are specifically unsafe. But the point is that energy storage systems are being deployed more and more. I was just looking at the Global Energy Storage Database, and there are now 1,200 projects in it, with big numbers of projects coming to fruition in California, New York, Texas, Hawaii, and other places. It's important to pay special considerations to safety. Next, please. So why energy storage safety? First of all, to reach full acceptance as a component of the electric grid, energy storage has to demonstrate a number of things. First of all, technical feasibility. The thing has to work. Second, competitive cost. It has to be able to be a part of the system and not at exorbitant rates. We need a regulatory framework. At the moment, we don't really have that as yet, but it's beginning to come into place. And then finally, and perhaps most importantly, we need safety. If we don't have safety, energy storage will not become a generally accepted tool of the utility grid. Just to remind you, the lack of safety endangers life. It leads to loss of property. It damages the provider's reputation. It leads to costly litigation, and it decreases confidence in the storage industry in general. I should also remind people that it's not just fires. There is also the possibility of chemical spills. Flywheels may explode. There's a danger of electrocution. an energy storage facility is a complex electrical, mechanical, and chemical setup, and safety shows up in, needs to be considered in all places. Next, please. Okay, so what has DOE done about energy storage safety? It's really an overarching concern that needs to involve many diverse partners. We put together a safety meeting in February 2014 to explore the space of energy storage safety. And we called in representatives from the national laboratories, from utility organizations like EPRI and ENRECA, the fire departments, firefighters, building commissions, insurance industry, and testing laboratories. All of those have a stake in energy storage safety. Then out of this group of people, and with their advice and help, we built the Energy Storage Safety Strategic Plan. This does not resolve the storage safety issue. It just lays out what needs to be done. Basically, the components are science-based safety validation techniques, incident preparedness, and safety documentations. So, next slide, please. We will look at these one by one. So, the first challenge area is science-based safety validation techniques. The stress is on validation and on science-based. And we need safety validation techniques for an entire storage system. This is critical as the deployment of energy storage systems expand. It's not components, it's not batteries or flywheels, it's the entire energy storage facility. So, we have a growing number of diverse systems. We really have no precedent for techniques that span the breadth of grid storage technology. These technologies are very different one from the other. The lithium battery is not like the vanadium flow battery, is not like a flywheel. So we need to develop techniques for assuring safety. We need to develop a science-based methodology to validate system safety. And these validation techniques not only must span across diverse technologies, but they have to go from micro to macro, because we need safety as much for a homeowner's energy storage linked with his rooftop solar as we need it for large multi-megawatt installations interacting with the grid. So, what do we need? Well, we have to focus R&D efforts on material science, on engineering controls and systems design. We need to do modeling. We need to do system testing. This is real system testing and the analysis of that testing. And we need to develop methodologies for commissioning systems and assuring field systems safety. Next, please. Okay, what do we do in case something does happen? Well, as with any large-scale deployed technology, there are risks. Unintended events could result in safety incidents. And they expose life, they have problems for the environment, and they put critical infrastructure at risk. So it's important to understand possible failure modes of the system and create plans to mitigate and deal with the potential for and the risk of these events as much as possible. So what are the gap areas? Well, there is fire suppression and protection systems. These are not the same for all systems. You don't just turn a fire hose on a lithium fire. That means we have to classify the various commodities involved. We have to verify and control stored energy. We have post-incident response and recovery. And we need first responder awareness and response practices. So first of all, that means we have to develop requirements for ensuring the safety of first and second responders, and then we can go from there. Next, please. Okay, what is called safety documentation is actually a complex area. In order to have safety measures be effective, the determination of the system, the documentation, and the verifications have to be standardized and specific to each chemistry, component, module, and deployment environment of each type of system. An urban situation is not at all the same as being out in the desert in Nevada. As I mentioned, lithium-ion batteries are not like flywheels. There are very specific codes and documentations that are necessary. This presents challenges. Crafting effective safety metrics and criteria requires recognition of at least two interconnected components: the stakeholders involved in the process and the complex and different documentation required for each component, module, system, and deployment environment. So, at the moment, there are many codes and regulations that have to be observed when energy storage is deployed in the field. The vast majority of these codes was not developed for energy storage, but for other situations. We need to take a look at all of these codes, and we need to either adjust them or create new codes to fit the energy storage field. Next slide, please. DOE, through its laboratories, is entertaining a number of projects which are geared towards safety. One of them is about mechanisms of component level safety. We are working at improving safety and reliability for long life cycle hybrid flow batteries by addressing the inherent failure modes of this chemistry. And of course, flow batteries come in all kinds of flavors. We are working on mechanisms of system-level safety. We are analyzing and improving the grid-scale energy storage as it connects to the system. And we have paid special attention to energy storage commissioning. And we are in the process of developing a commissioning manual that will be published online to provide support for the industry by increasing the safety and decreasing the cost of new energy storage installations. Next, please. There are publications that are already available through the Sandia website. There is a directory of applicable codes. As I was saying, these are not engineered to apply to energy storage systems, but nonetheless they must be obeyed by all energy storage systems which a vendor would like to deploy. We have a general manual on storage safety, Storage 101, and we have a storage performance protocol that defines on how one should measure the performance of an energy storage system for a given situation. Now, where do we need to go? Well, we need to develop a framework for risk assessment. We need to do technical research on a number of topics. We need to engage in life cycle safety testing. You can't just look at a system and say, well, it's safe now. You have to realistically test it for a long period of time or an accelerated testing regime in order to develop life cycle safety. As mentioned a number of times, existing codes, standards, and regulations are not geared towards energy storage safety, and we need to develop a whole body of codes based on experience and results that will apply to energy storage. We need to develop criteria which guarantee the safety of first and second responders, including post-event recommissioning or decommissioning as necessary. And finally, we would like to develop a comprehensive information resource to serve as a clearinghouse of related reports and information, share progress in activities, and document relevant safety incidences and off-normal events that are reported for deployed systems. And with that, I conclude, and the different topics are going to be treated by experts who have offered to make a presentation. Thank you very much.
Okay, and thank you very much, Imre. I'm going to go ahead and introduce the next speaker. I just want to remind everybody, please do get your questions in. We have 138 people on this webinar at the moment, and we will do our best to get to as many questions as we can, but you do have to send them in. Just type them into your question console on the screen. Okay, so the next presentation is from Dr. Sean Hearne, Manager of the Energy Storage Technology and Systems Department at Sandia National Laboratories in Albuquerque, New Mexico. And I will pass it over to Sean.
Thank you, Todd. Okay, so I'll be discussing validation techniques for energy storage safety, and a lot of this comes from the strategic plan that was recently published. So a good place to start is discussing what do we really mean by safety validation, and why is it important? Imre certainly touched on this, that with any system where you're storing energy, there's a potential for an unintended release of that energy. And how that actually occurs can be a matter of safety, this release. So there's a deliberate release of the energy, but then you can imagine with a grid storage system the possibility of arcing or combustion or mechanical failure as a number of possibilities. So in the validation, you have to look for what are the possible failure modes, how you would mitigate those in the case of a accidental release of the energy. So what is currently being done is the next big question. And if you look around the energy storage industry, a lot of the work is really being leveraged out of what's been done in the vehicle community, particularly for the lithium-ion world for vehicles. And so those tests are cell-level tests primarily, occasionally some module-level tests, but they're around crushing or burning or doing over-voltage tests for abuse conditions. So it certainly does look at a number of the possibilities, but it doesn't really address the full suite of possibilities for failure modes for grid storage systems, and is also very much limited to a few technologies. So what's done currently in many cases is that the systems are built with very large engineering margins, so that if a failure, so to mitigate that chance of failure. So essentially the systems have to be dramatically overbuilt, because there's this lack of fundamental knowledge of what are all the failure modes and how you would mitigate them as best as possible. So the shortcomings of doing this are fairly obvious. Well, you certainly make the system more expensive than it needs to be. It's a lot of very time-consuming. Large systems themselves are very difficult to test. So how do you meaningfully do that? And there's currently a difficulty in predicting for untested failure modes. So there's failure modes that may not be obvious, that because of we are only testing for very specific items, so you may have other mechanisms active. And so the end result of all of this is that there's, as Vince will be talking about in a moment, there's very few codes and standards for safety of grid-scale energy storage systems. So what's needed? Well, as Dr. Gyuk mentioned earlier, certainly the scientific basis for safety is a critical piece. This validating of engineering controls and system design, predictive models for the safety, and then finally all of that being rolled into the testing and analysis protocols for safety. So I'm going to spend the next couple of slides going a little bit more detail what we really mean by these four topic areas. So the scientific basis for safety, obviously failure of a system is going to start at interfaces or at the materials level and then grow throughout, so cascading through it. So we have to have a fundamental understanding of what are the possible ways that a system can fail, and so what are the active processes. So you consider looking at materials level, so looking at the electrolyte or the anode and cathode, or catholyte if it's a flow battery, and how those different materials will fail. Then when you roll that up to the next higher level into the devices. So with a device, dielectric breakdown or manufacturing defects, how those all play into it. So there's a number of key questions that need to be addressed when you're thinking about this scientific basis for safety. And that's, as already mentioned, this: what are the failure modes? And ultimately, what are the boundaries of operation that you can have with these materials and then these devices, and then it'll show later about the overall systems. And so all of that goes back to what are these active processes and how can they be optimized or improved. This is not a one-way street when you're looking at the materials. As you start to identify failure mechanisms at the materials level, you can start to engineer and expand the operating envelope of the system. So you can actually improve the performance characteristics. Now, on the engineering controls and system design, as I said, a lot of the work currently has been on individual cells, and so this leaves a gap in terms of the larger scale system, the fully integrated, as Imre was discussing. You really need to be able to look at how these cells are attached, or control systems, or the power electronics, what role they play in, or the black starts apparatus. You know, and there's a number of things that clearly come out in terms of separations of cells within modules or flow systems. And one of the things that was also mentioned was, what are the fire suppression systems and techniques? Because that's all considered within this engineering system design. So going into these key questions from the system level, looking at the circuitry, the plumbing, pumps, and tanks, you know, because there's obviously, with a flow battery, there can be thousands or tens of thousands of gallons of analyte and catholyte, and so you need to be able to be prepared if there is a spill, or how you can best improve those so they're as safe as possible. Cascading failure, that's clearly another area. So it may be that unrelated systems can cascade together, causing a safety incident. And one area I really want to highlight that we in general haven't talked a lot about, it's software and control architectures. So the software is very often one of the last components to be put together to operate a system. But with the storage, it really is a critical safety component. So understanding how that software plays a role in the overall system safety is absolutely critical, and being able to validate that you have, in fact, accounted for all possible modes of failure of the software and what that will have on the overall system. So again, it's this holistic view of what does safety mean in the storage system. It's not a big black box with two wires sticking out of it. So that then leads into the predictive modeling. So you need to be able to understand at the materials level and the cell level and develop models so that you can predict what's going to be happening at the large scale. You can certainly, validation at the large scale is critically important of these models, but at the same time, we're not going to be able to destructively test every system that gets fielded because obviously we wouldn't have any systems left. But you need to have techniques put in place that are validated and that we have high confidence in that can predict the ultimate safety of the fully integrated systems that go into the field. So I have two examples down at the bottom here of the page, one looking at thermal modeling within a battery cell and connecting that to the voltage and so the applied voltage to it. And then looking out to the larger length scales, the next is an example of what happens when you have racks. And if there was an ignition source in between the racks, how do you best design the system to account for the heat transfer, the smoke within the system? And the last, as we're talking about, is rolling all of this together into validated testing and analysis protocols, because it's really these protocols which will be codified into the codes and standards. So with the testing methodologies and the electric vehicles that we're really looking at right now, you can think about electrical tests, the mechanical, the environmental. That's sort of where it's been fairly limited. We need to obviously branch out from that. So we need to go further than what's in the lithium-ion community and develop these tests that account for significant differences, for example, of the build site. If you have a system that is built on site, then a lot of the safety protocols and testing that's done, or codes and standards that are the system is being built against, are being implemented by the fire marshal or looking at that direct community doing the building. Whereas if you have a system that's fabricated in a factory and you ship it out, then it's a system that would be more likely to be, say, for example, certified by UL or DNVGL. So you have very different standards and ways of approaching safety in those systems, just based off of where it is built and how it is designed. As Imre had mentioned, there's a huge variety of different technologies out there, and that's part of the complication of storage, grid storage safety, is you have this wide variety of technologies. You're not going to necessarily have the same testing protocols for a flywheel as you would with a sodium battery, because you have dramatically different operational conditions for those two systems. And finally, all of this needs to be linked back to this safety basis, or this scientific basis for energy storage safety. So as a concluding slide, just a couple of take-home points that I want you to walk away with. And you know, we need tests that validate the safety of a system that have to be rooted in a scientific basis. So you have to have this understanding of what's occurring at the materials and being able to scale that up through modeling or specific tests. And that's actually what the point of the next bullet is. This tests need to be limited in scope. We're not going to be testing every aspect. Color of the container is not going to necessarily impact the safety of the system, but you have to ensure that the tests that are put in place and the protocols that are developed are sufficient and provide the confidence that's needed by the consumer, by the utility, by the regulator. And so the end note here is that there's still significant work that needs to be done in developing what are these most efficient and cost-effective testing protocols. And with that, I will conclude and hand over to the next speaker.
Okay, thank you very much, Sean. The next speaker is Kenneth Willette, Division Manager of the Public Fire Protection Division of the National Fire Protection Association. Do we have Mr. Willette's slides? There we go. Okay, please go ahead.
Thank you very much. Hello, everybody. This is Ken Willette from NFPA. And you'll notice on this slide that Matt Pace, captain on San Jose Fire and representing the International Association of Firefighters, is also referenced. He and I have worked together on this project. We both attended the February meeting out in Albuquerque that was helping inform the Energy Storage Safety Strategic Plan, and we've worked together on the responder issue. And this is an important issue both for NFPA and the IAFF in that Responders are that first line of defense at the local level who, in spite of whatever best efforts have taken place, will have to deal with these systems when there's an unforeseen event. And while we consider this to be a low occurrence event, it does have high risk. And my comments today are based on trying to close the gap in information and knowledge that responders need so that when they respond to these low-frequency events with correct information, they can make informed decisions and minimize the damage to the energy storage system, minimize the damage to the facility, but more important, protect the greater community against any risk. And what this does is provide confidence when these systems are situated in any type of occupancy that the public can turn to the responders and ask the question, can you assist us, can you protect us if there is an event here? And that's the goal of my comments today. What is really needed and was identified as a gap through the Albuquerque workshop and in the subsequent report that came out in December of 2014 is that a basic understanding of energy storage systems by the responder community. And while these may seem to be complex, when you break them down to their smaller components, one of the most challenging features of these systems is the new technologies and the chemistries that are being utilized. If all we were looking at was a lithium-ion based system, it would be relatively easy to characterize the risk, to talk about what we could expect if there was an event, and to discuss response strategies and tactics. But the truth is that is just one of a handful of chemistries, and each chemistry presents its own challenge. And understanding those challenges and putting them into some kind of organized format for responders to be able to consider as they evaluate an event and they consider the risk management as they go into operating at the event is proven to be a bit of a challenge. And if you're familiar with the responder community, you might be aware that when it comes to dealing with hazardous materials, there is the yellow DOT guidebook, which is in almost every piece of fire apparatus, ambulance, and police vehicle in the United States. And that took a very complex library of chemicals and broke it down into some standard descriptors and a standard system of identification through numerical placards, and then related that to standardized guides for addressing these types of chemicals during an event for the first 5 to 10 minutes until more technical assistance could be brought to the scene or the incident began to develop its own nature and the responders would have to deal with that. That's the approach that the fire service in particular, but all responders, really need to give them a foundation for safe response. The ability to categorize these systems, the ability to understand the relative risk in each category of the system, and then to develop appropriate response methodologies. The application of codes, standards, and regulations is really fundamental to the responder community on 2 levels. One level is for the authority having jurisdiction. That might be the local permitting authority within the fire department or some other agency, but is going to be working with the developer of this energy storage system for permitting and meeting other requirements to ensure it meets the best intentions of that jurisdiction in providing safety against existing codes and standards. But what it means for those responders who are going to be called to operate in that environment is an understanding that there are some guidelines in place that provide not only for their safety, but for the safety of the building and the safety of the greater public, and they will want to utilize those safety features. They will want to leverage the benefit they bring to the event and to build off of them so that they can manage the event safely. Critical to understanding the energy storage systems is the commodity classification piece. And within the codes and standards environment, that's fundamental within NFPA, because our NFPA 13, the standard on fire sprinkler systems, refers to commodity classification as the first step that must be taken in determining the appropriate type of fire suppression sprinkler system for an occupancy based on that. Currently, lithium-ion is not recognized by NFPA 13. So what that does is it leaves a gap. It leaves a gap for those who are trying to site these facilities, for their fire protection engineers, as they attempt to design appropriate suppression systems, for the local authority having jurisdiction as they attempt to do the necessary permitting. that they cannot point to one standard and say we have the appropriate fire suppression sprinkler system. And that is further complicated, as I just mentioned previously, about the variety of chemistries. Now, it's not an insurmountable challenge. It can be accomplished through research, through further testing and modeling, and through field tests. And as that information becomes available and informs the standards, it will close that gap. But right now, that is definitely a gap. There has been testing on the lithium-ion batteries, but it's been focused mainly on consumer battery storage and on electric vehicle batteries. NFPA has done both of those projects, as have other standards developers and research laboratories. In the consumer battery storage, because these are stored in a warehouse, then a water-based fire suppression system is the norm. And the research has shown that with some modifications, that system can provide some protection. But when we put the batteries into an electric vehicle, and we're looking at somewhere around a 300-volt battery, and based on our actual field fire tests, what we discovered, if water is to be used as a suppression agent, it is the most commonly available suppression agent for the fire service across America, and it is the one that is easiest to apply. It has to be there in sufficient quantities to provide, we use the term, copious amounts of water. For a single battery in our live burn demonstration, the amount of water needed went from 269 gallons to over 2,600 gallons. And for the fire service, that presents a challenge because the tank on a standard fire engine is probably in the 750 to 1,000 gallon range. And the minute you exceed that, it mandates that you either get a water supply through a fire hydrant system or by shuttling it to the scene through tankers or other means of portable water supplies. So if we're looking at an energy storage system, lithium-ion battery, that could be X times larger than an electric vehicle battery, the amount of water, of course, stands to increase. So bringing that into consideration for the responder community, it's an important piece of pre-planning and operational planning. The other challenge for the responder community is the expanded applications. Lithium-ion batteries and the technology has been there for many years, starting in consumer applications, but we've seen the expansion to more applications, including residential applications, where they're being used in conjunction with solar systems, and also to high-rise structures. In the city of New York, there is a concerted effort underway to bring energy storage systems into high-rise structures to help meet the energy management demand within the structure and within the greater grid. And the challenge that poses is the building was never designed for that type of risk at the time it was designed. And what features, what fire protection features, what fire suppression features need to be included, but additionally, what training for the fire service and other responders to be able to safely and effectively manage an event. And I made a comment about the amount of water utilized for an electric vehicle battery, and that's outside. Discharging 2,000 gallons of water outside allows it to flow into the natural landscape and to be absorbed and drained away. But if you're flowing thousands of gallons of water in a high-rise structure, you have to ask yourself the question, can the building hold the water? Where will the water go? How can they control it? And is there anything to be concerned about in the runoff? So as these systems get expanded application, it raises new questions. And lastly, we're seeing energy storage systems in commercial structures, both from a microgrid perspective, where it's on-site but external to the building, as well as internal to the building. So one of the key elements in preparing the responder community is empowering them to be able to do pre-planning and risk analysis. And that happens through awareness training, providing good information, and then doing site inspections to actually visit the energy storage system, to talk to the technical experts who support the system and to gain knowledge from them, but also to find out how they can be available to be technical advisors to the incident commanders during an actual event. This is critical for the education of first responders, and the first responders have demonstrated many times the ability to adapt to new technologies and the challenges they face, provided they're giving the information to do it. And I would make a comparison to how the responder community has adopted the electric vehicles that are now making their way into the American consumers' garages and roadways. And that was done through a concerted effort of bringing awareness to the fire and emergency medical services and law enforcement community in a manner that's available and acceptable, and updating that with research as it becomes available, and considering other vehicles to provide them the full suite of information. What that has done is made responders empowered to deal with these situations in a safe and professional manner. The other component of this is as they analyze the results of this training and education and discussion with the technical experts, they can determine what is the appropriate level of response for that location and for that system. And while you don't want to under-respond, you certainly don't want to over-respond. Sometimes an over-response can drive a least positive income because you have folks who may not be aware or may not be the right resource and may struggle to find a correct response to the problem they face. Whereas if you dispatch the correct amount of responders with the correct technical knowledge in the tools, then you have a better chance of maintaining the incident at the lowest level possible, providing for the safety of all, as well as protecting the system and the facility. So education, awareness, pre-planning, and risk analysis are critical to ensuring responder safety and effectiveness in dealing with emergency energy storage systems. The Energy Storage Safety Strategic Plan that was released in December of 2014 on page 47 identified these gap areas specific to the responders. And for those responders who might be on the webinar today, I encourage you to access that report. There are several chapters that focus exclusively on responder issues and the gaps. And the Department of Energy is to be commended for bringing responders into the discussion at this early point to inform the process going forward and for being identified as critical to the safe deployment of energy storage systems. And the 5 gap areas were fire suppression and protection systems. And I think between my comments and previous presenters, we've covered that pretty adequately. And commodity classification as well as the appropriate suppression system are key components. And as you'll know, commodity classification appears again. That is really important to give responders the knowledge base to be able to manage the event. Verification and control of stored energy, and Dr. Gyuk mentioned that in his opening presentation, but knowing what is the state of charge within the energy storage system, is there stranded energy, are there mechanisms to be able to control it or to discharge it safely, will be critical to responders being able to interact with these systems and manage an event. Post-incident response and recovery. After the incident is over, there's going to be returning to normalcy. How do we bring the system, more importantly, how do we bring the structure back to a safe condition? How do we bring the responders back to a safe condition? Are there concerns about exposure to their protective clothing, concerns about exposure to their equipment that will require either decontamination or some other means of preventative controls? And recovering from the event, how do we get the electrical grid in that system back to normalcy to ensure that critical infrastructure is protected, as well as the building and the energy storage system? And as I mentioned on the previous slide, the first responder awareness and response practices are critical to this. And again, I commend the work of the Department of Energy and Sandia and the participants in the Albuquerque workshop for validating that through the report and bringing it forward through the webinar today, but also into the future as we address the needs of the United States and the responder community for energy storage systems. So I'd like to thank everyone for your attention.
Okay, and thank you, Ken, for that presentation. We are about to go to our 4th and final presenter for today. I just want to remind everybody we have a large number of people on the webinar. We do have an hour and a half today, so we will be able to get to your questions, at least a good number of them. We have some questions, and they're good ones, but we have room for more. So please type your questions in and or comments, and we will get to them as we can. So our final presenter for today is Dr. Vincent Sprenkle, manager of the Electrochemical Materials and Systems Group at Pacific Northwest National Laboratory. Vince, you ready to go?
Yeah, I am. Thanks, Todd.
Okay.
All right. There we have it. So, as you've seen in the other presentations here, this is really a coordinated effort, and when you look at that diagram up in the upper right, it's a multi-pronged approach from the science and understanding of safety, from the incident preparedness, but also in terms of the codes and standards. And so at that February meeting, there were a lot of comments and concerns about the current state of codes and standards. And so in a lot of cases, there were, as we've mentioned before in the previous talks, there's incomplete or the codes didn't cover it. And so, let me back up one. A lot of the things that came out and are documented in the energy storage safety strategy is just the speed at which the energy storage technologies are being applied and also new technologies growing. The current code standards and regulations, or CSRs, really don't cover a lot of the new technologies and really lag, in almost any technology, lag the development and deployment of new technologies. And so if there are codes and standards out there, they're traditionally focused on the more traditional systems. And so the additional guidance is needed. And so there's a continual process needed to update and keep abreast of those advances. There's also the need for research in these systems for assessing the overall system safety, and then making sure that information gets back into the codes and standards. So it's both looking at the code areas to see if there's gaps in the research and then getting that information to the standards. And so one of the current issues with a lot of these is the codes for the ESS deployment is assessed on a case-by-case basis. And so you end up going through and pulling together what the local standards are in order to get that system deployed. And so, one of the topics that came out was the need to get, a more uniform understanding of the overall system. And then where we have these systems, so through the ARA projects and other demonstrations, as Todd had pointed out earlier, we have installed systems out there. And then to try to get those key experiences with implementing the system, get those documented and out to the community. And so the final one is just to keep the codes and standards updated and bringing together all the critical stakeholders to make sure that we are addressing this holistically as we move forward. And so out of that meeting really came kind of a first action plan. And so Dave Conover at P&L was able to spearhead this and pull together a group of stakeholders, hopefully many are on the phone today, to try to take a shot at working on these initial issues. And so in that regard, in the October time frame, October 2014, released the first two documents that's serving as an initial step in addressing these codes and standards issue. So the first document is the Codes and Standards Overview. And the overall objective of that document is simply to provide an understanding of the process. And so this is geared towards people who may be for the first time looking at codes and standards, who may be doing an initial or deployment of a system. And so it basically goes through and spends time looking at what's the importance of codes and standards, where are the codes and standards coming from, so be able to provide more depth on that and an understanding of the CSRs. And really the goal was to enhance the communication and start to get that collaboration that we need. As we said, this is going to be a multi-pronged problem in terms of codes and standards, and there has to be input from all stakeholders. The second document that came out of this in October of 14 was the Codes and Standards Inventory. And so the goal was this document was, at this point in time, where are we? What are the pertinent codes and standards that may be impacting your system? And so that document went through and actually identified most of the current codes and standards related to safety. The second part of that was those installations that are already out there and those experiences that people have had. What has been their challenges with codes and standards? So trying to bring those use cases and what people have already faced to light. How did they deal with the gaps in the areas? And so there, in the second section of that document is those user experiences. And then the other aspect of this was, how do you go through and secure the approval where the codes and standards may not apply? How do you do the equivalency arguments for the codes and standards? And then start to identify the gaps that there currently are in the storage technology and the standards. And so this is where we start moving forward. So really the 2 points of the document were to establish our baseline for where we're at now, and then help to really identify where we need to go in these codes and standards. So in the next steps, what we're going to be looking at over the next few years, tends to be short-term goals and long-term goals. As we get into this on the codes and standards, these are multi-year processes, in order to change a standard and get something implemented. And so there's, areas where we can have immediate impact to try to do that, but areas where we need to be looking out 3-5 years down the road. And so key right now is bringing together those stakeholders to start identifying the gaps in the technology and the codes and standards. Other aspects are looking at developing templates for a typical ESS storage installation and document the codes and standards. So if you have a reoccurring system, that's going into, say, an urban area with this population density, that can be more of a template and saying these are the requirements that you have to have. So every time we go in with a new technology and a new application, we're not having to go back and build from the ground up. And then identifying those areas for the short term where research is still needed in order us to be able to fully fill out the standard. And so some of the opportunities you can see on the slide here are coming out. There's been efforts to support the new Article 406 for the National Electrical Code, participation in UL 9540 on energy storage system safety. Those are ones that are ongoing, and Dave's been working with people to try to address those. But then you start looking out long term. So the International Fire Code proposed changes are due in January of 2016. Proposed changes to the IEEE Electrical Safety Code are due in 2019. And so that's where we start looking at these long-term things that need a coordinated effort now in order to have reasonable proposed changes to these systems when they're up for looking at again. And then also looking at all the other different systems, and this is larger than just DOE being able to do this by themselves. And then so as you build up the stakeholder organization to start looking at these, we need to continually track and support the needs for the revisions. And then also, how is keep abreast of how the technology is evolving over time. And as new things are going to come about, we have to continually look at those things and develop basic a feedback loop between the technology development and the standards and how that impact is going to be felt. And then also keep looking at identifying the research and opportunities for new standards. And then the key thing here, I think, overall, is how do we keep this updated? How do we keep the community together? And so that becomes a key factor as we move forward, is getting everyone on the same page and working together so that we can ensure the safe deployment of these storage systems. And so that's the last slide I had. Thank you.
Okay, and thank you very much for that. We have, I think, now heard from all four presenters, and I think we do have a number of questions, so I will go ahead and dive into those. Some of them will be sort of open for whoever thinks they would like to address them, and some will be obviously directed toward a particular presenter. So I think we have one here for Ken. The question is, when you say risk analysis, what precisely do you mean? How detailed is this analysis in similar industries? Is a requirement for this analysis in a code or standard somewhere, whether in energy storage or in another industry?
Sure. Very good question. And when I referred to risk analysis, I was referring to it in two ways. One, in the pre-planning phase, so that when the local response agency looks at its resources and looks at what the event might be, they make an estimate what is the risk to the individual responders and the risk to the community, and use that as a tool to help guide them as to how involved they can be in the response, or do they need to take an offensive approach where they can directly engage, or a defensive approach where they need to protect and await the arrival of other technical experts. The second way I referred to it was on scene, that the role of the incident commander, which is the official that's in charge of the responder activities, for example, if there's a fire, it would be the highest ranking fire officer typically, that as they're engaging with the event and they're deploying their resources, they're constantly making that risk analysis, looking for changes in the situation. For example, it might be how the energy storage system is reacting to the application of water. It could be an off-gassing event with the potential for a thermal runaway. It could be just an unusual occurrence that somebody decided to call 911 to have further investigated. And as the incident commander is monitoring the situation, he's constantly pulling that information into his thinking and updating his risk analysis. So that was the point, the way I referred to it. In terms of, is it required by code within the responder community, the simple answer is no. But we do have one standard, NFPA 1500, which is the occupational safety and health standard for the fire service and emergency responders, which does recommend that a risk analysis be performed for these type of unusual events, these low frequency but yet high risk events. So that would be my answer.
Okay, thank you very much. This is a interesting question. Do we have a list of incidents recorded related to energy storage safety issues and the severity of whatever issue it was? Is there any? Does anyone know? Is there some kind of recorded list or database of incidents that have actually occurred?
This is Sean. I don't believe of any public list that has come out at this point, but maybe one of the other speakers has more knowledge than I.
Yeah, this is Ken. I just attended the UL Battery Safety Summit, and several presenters there commented on more towards occurrences with lithium-ion batteries. There were relatively few that dealt with energy storage systems. In fact, there's only one that comes to mind, and that was over in Hawaii at the wind farm, but that was lead acid. And that's the only one that was identified at the UL Battery Summit.
Actually, there were more than that, and people in the community are aware of them. But Generally, they are not documented because the vendor probably would not like to have a public document that where they can be held liable.
Okay. Another question. What are the target dates for the UL 9540 and the NEC 706 to be in effect? And maybe whoever addresses this can identify what those refer to.
Yeah, I don't know the dates off the top of my head. Let me look here. But NFPA 790 are due July 6th of 2015. And then several proposed changes to IBC, and those are due January. Well, it's already passed. That was due in 15. So yeah, I don't have a good date on that.
Okay. Here's a question about how this effort is going to go forward. Do you plan to validate testing protocols developed by energy storage vendors, establish your own expertise in each storage technology, or some combination of the two? Please explain how you see this developing.
Let's see. So this is Sean. I'll take a crack at that. So I certainly agree that each technology is going to need to have some consideration in terms of what are the best validation protocols to be used and to be developed. Certainly Sandia and DOE and PNNL, I mean, we don't typically issue standards per se, so that would be done by some other body, and the protocols that would be done, as have been done in the past, have been done in conjunction with different bodies that are in different interested parties. So it would certainly be a community effort that I would see in developing the exact testing protocols that would come out.
Okay, thank you. I want to just mention again, because I have several questions from people wanting to know if they can get copies of the presentations. The entire webinar will be archived on our website, and we will actually, Samantha, maybe you can put that slide up now that shows the URL for that, so people can go later and get the archived version. Okay, next question. Has work been done to address the possibility of accidents involving the air-gas mix when storing compressed air in a depleted gas well? Has the use of nitrogen been explored as a way to extinguish fire from air-gas mix?
Okay, I'll take that one. There have been limited experiments in the flammability of the gas-air mix when you insert gas, when you insert air into an exhausted gas well. The results generally have shown that this is not the case. The situation does not lead to any kind of explosion or fire or whatever it is. However, extensive tests have not really been performed. That is one area that definitely should be looked into, and in both laboratory experiments and experiments in the field.
Okay, very good. A couple of people have commented on earlier questions. One person saying the answer to the question on the 706 and 9540 standards, the NEC 2017 publication, and then adoption through state and local processes. Same with UL 9540, but the publication will be when UL completes consensus process to develop the standard. So that's addressing one question. And then the same person also wrote, for questions related to the development adoption, etc. of processes associated with CSR, see the Codes 101 document that Vince mentioned. So thank you very much for that. Okay, so here's a question. Is a modular approach being taken in establishing energy storage safety standards? For example, the safety requirements of a remote ISO container of batteries should be different than a pack of batteries in a commercial or residential building. And the questioner goes on with other examples of this. So the question is a modular approach being taken to the standards?
I think the overall goal is, yes, that you have to, and that's part of the goal of trying to develop templates, you know, so that it is more of an application specific. And so you will have the underlying standards for the actual, maybe the chemistry that are specific, but the overriding one is, you know, if it's a modular system that's isolated, you know, at a substation, then there's going to be a set of standards. So that's kind of the overall goal in looking at that.
Okay. What are the fire suppressant systems used in large-scale lithium-ion battery-based energy storage systems?
So Ken, can I actually defer that one to you? This is Sean. I think you're better positioned to answer it.
Sure. I don't have a definitive answer for that. At this point, as I mentioned earlier, it's a case-by-case application. Anecdotal evidence has been that there's been folks using a myriad of systems, from trying to use a water-based fire suppression system to using a gaseous agent suppression system. But at this point, there's nothing that you can point directly to and find it appearing directly within the NFPA codes. NFPA 850, which deals with power generation plants and provides recommended practices for fire suppression and protection within electrical plants, does have some guidance on it, but again, a lot of it is left to the chemistry and to the site conditions.
Okay, thank you. I think this is a follow-up to that question from the same person. Do you have any comments on the field data related to fire suppressant system effectiveness?
Yeah, I'm in the responder group, not in the fire suppression systems group, so unfortunately I can't comment on that. I haven't seen that data.
Okay. Is anybody else interested in commenting on that question? Okay.
I think that goes back to the original question of it'd be nice to have a list of all the incidents and how what the impacts were, but that will be something I would say be hard to pull together.
Okay, good. Here's a question on codes. Is the group considering code change proposals to the IBC and IFC, I'm assuming that's building codes and fire codes, to address the technology and hazards for energy storage systems?
Yeah, there are. I mean, those are codes that are on our radar in terms of addressing. You know, really the first step is trying to make sure that we get the actual stakeholder community together and see who's best to tackle those different codes. So there's a multitude of different ones that still need to be addressed to make sure storage is not limited in terms of going into an area and can be safely deployed. You know, those will have to be done in time, and so hopefully in the next year you start to see that development of the working groups around codes and standards, and then have a subgroup that will tackle the building code in that area. So it is on the radar. It's still a work in progress.
And
okay, thank you.
Just a real-world example of that, in the city of New York, when they were preparing for the energy storage systems to go into structures, they had to look at the New York City Fire Code, which is a derivative of the International Fire Code, but is their city-specific code. And they needed to add some additional chemistries within the allowable chemistries for battery and energy storage systems, the lithium-ion and others. And it did increase some of the storage quantities of those chemicals in that chemistry mix. And in comparison to the NFPA-1, the NFPA fire code, they've increased their storage capacities to recognize the systems that might be coming in.
Okay, thank you. I have an email from Dan Borneo from Sandia Laboratories. He says, I believe FM200 is being used for lithium-ion fire suppression. I don't know what FM200 is. Maybe somebody on the line can fill us in on that. Does anybody know what FM200 is?
Yeah, this is Ken, and I'm drawing a blank on it, unfortunately.
Okay. So we'll move on, and maybe we'll get another email from Dan to enlighten us on that, on what that is. Well, I have a question that I kind of wanted to ask, and I don't. Doesn't seem to be coming up, so I'm just going to ask it. You know, one of the major issues with regard to new technologies, and such as energy storage, is cost. And of course, costs tend to come down over time, but then codes and standards can sometimes have an opposite effect. How do you see this going forward affecting costs for energy storage? And do you have any thoughts on that aspect of it from a customer's point of view?
So this is Sean. Just a quick statement
Yeah,
regarding the validation tests. And so one of the things which I did mention during my portion was that as you start to develop an understanding of what are actually all of the failure modes and the processes, you can decrease your engineering margins so you don't have to overbuild the systems. So the end goal would hopefully be to reduce the cost of the system through this understanding. And so with that, I'll hand it off to my colleagues.
Yeah, I would just say I think one of our goals has been, we've seen in other industries where the codes and standards lags the technology, by a great degree, and then your cost increases because you have to go back and re-engineer for that application. So one of our goals has been to get this, maybe get ahead of the curve a little bit in terms of the codes and standards implementation. And so hopefully by developing those in parallel with the technology, you will, reduce the need to re-engineer or to get it into an application. So that is one of the goals by having this as part of the plan now.
Okay, great, thank you. Well, we've gotten about 100 people sending me messages explaining what FM200 is. Apparently, it is a DuPont product. It's waterless fire suppressant, chemical-based fire suppressant, and somebody said it's also known as HFC 227. Anyway, it's a clean, waterless chemical fire suppressant. So thank you to everyone who sent that information in. Okay, so somebody wants to know what prompted this effort. The questioner says, is there now a critical mass of energy storage, or was there an incident that catalyzed concern on this topic?
I'll take that one. No, the main driver is in fact the critical number of energy storage installations. I mean, there was a time when you could count the number of storage installations, and I knew them all by heart. With various mandates and with the interest in energy storage applications on all levels increasing rapidly, we realized that somebody has to sit down and worry about the safety of the installations. Also, a large number of companies many of them not based in the United States, were getting into the game. And again, it was not obvious to what degree companies would be safety conscious. Many of the big companies are indeed very much aware of the issue, but without codes and standards and without a general understanding of and guidelines for how to do safety, we really are at the mercy of people's goodwill. And so we decided it was time to put a safety initiative into effect. Now, of course, we have to wait whether we can get the funding to do that. So, pray.
Okay, thank you. Somebody wants to know what the time frame is for the near-term CSR goals set out in the strategic plan, specifically a description of how codes and standards relevant to energy storage are structured and used. Will be prepared as a primer on ESS CSR.
Vince?
Anybody?
Yeah, Todd, this is Ken, and just from the NFPA perspective, we have several of our NFPA committees, including the NEC. I believe it was mentioned earlier, Article 706, I believe. We also have NFPA 850, NFPA 13. They're all looking at energy storage systems. In some, they actually have proposals. The NEC, for example, which is meeting this week as we speak, in their first draft meeting, is considering proposals to include additional language for energy storage systems. And NFPA 13 and 8 has a chapter reserved for future consideration. NFPA 850 has a task group that's looking at it. So it is being recognized and it is being addressed by a select group of standards.
Okay, thank you. A question that comes up sort of as a result of what Imre just mentioned, that fact that, there are a large number of energy storage systems that are out there now in use, and more being installed, it seems, every day. So although we have this effort going forward, we also have products actually, on the market and commercialized. What are the customers or communities that are going to be hosting these systems? What do they need to know now, and what's the current state of the art? Are these systems coming with a set of safety instructions for community responders? Are the insurance companies aware of what the concerns might be in terms of installation or safety measures that should be taken around the site? Or what's the current status?
Todd, this is Ken, and I can just share anecdotal information from two areas. One, from talking with different manufacturers of these systems at various conferences, and second, our recent conversation with the folks at the fire department in New York. And it is, I think you hit the nail on the head. It's a customized location-by-location approach. There is no standard. We heard discussed earlier, perhaps one of the gaps and a solution to the gap was providing templates that would guide for the installation, the commissioning, and making that bridge between the responder and the local installer of the system. But that's not there right now. So it is very much a customized approach, and it can vary and be all over the board, from great dialogue from the time it's conceived to the time it's developed and cited and commissioned, to no dialogue at all.
Yeah, I can support this. In any project that DOE has supported, I have always tried to insist that the the company that's building it, or the utility that's building it, stay in contact with the local fire authorities and give them a walkthrough of the facility and so on. And in some cases, the local fire chief sat right there on the platform during the commissioning, along with the mayor and all the people involved in putting up the unit. In other cases, the owner of the system told me that, oh, they took care of that, no need to involve the community. So that's my anecdotes.
Okay, well, thank you very much. We are coming up on 4 o'clock, and I want to give everyone a chance for any last thoughts or comments. We've addressed a good number of questions. We have a few more that we didn't get to, but I think given that this is an hour-and-a-half webinar, we ought not to stretch it out any further. Any final comments or thoughts from the presenters?
Well, I would like to say that I find the response by the community very heartening. People from various organizations, EPRI, NEMA, and so on, have been very appreciative and have collaborated and contributed greatly. I find the association with the firefighting community extremely important. And the general response to both our strategic safety plan and to this webinar, I think, is heartening. I just hope we will be able to continue this involvement and be part of future codes and future best procedures as time goes along. Thank you.
And thank you. Anybody else? Okay. I want to make sure that folks know where to go to access relevant documents from DOE or Sandia or PNNL or others. If we have a URL or a general address that you can give out.
Yeah, so the website where you can find all of the DOE electricity storage documents is at sandia.gov/ESS.